American engineers between 1892 and 1900 completed an engineering project that no modern team has ever replicated. They reversed the flow of the Chicago River. The project cut 28 miles through Niagara limestone bedrock and moved 43 million cubic yards of earth and rock by hand. 8,500 workers built it under Chief Engineer Isham Randolph. On January 2, 1900, the canal opened. The river reversed direction. The typhoid death rate in Chicago dropped from 174 per 100,000 to 14 per 100,000 within a decade. The river is still flowing backwards today. The Chicago River reversal is the most extraordinary engineering achievement of the late 19th century in the United States. The project does not have the public fame of the Panama Canal or the Brooklyn Bridge or the Hoover Dam. Few Americans today know that Chicago reversed the flow of its river. Fewer still know how the reversal was accomplished or why it was necessary. The reversals was the engineering precondition for Chicago's emergence as a major American city. Without the reversal, Chicago would have been killed by its own sewage. The river reversal solved the sewage problem by reversing the direction of water flow so that Chicago's wastewater no longer contaminated Lake Michigan, which was the city's drinking water source. The reversal worked. The river has been flowing the wrong direction for 125 years. The problem that necessitated the reversal was sanitation. Chicago in the 1880s was a rapidly growing industrial city with a population approaching 1 million people. The city sat on the southwest shore of Lake Michigan at the mouth of the Chicago River. The Chicago River flowed naturally from west to east, draining the surrounding flat prairie land into Lake Michigan. Chicago's wastewater entered the Chicago River through the city's expanding sewer system. The wastewater then flowed into Lake Michigan, which was Chicago's drinking water source. The wastewater contaminated the drinking water. Typhoid fever and cholera became endemic in Chicago by the 1880s. The death rate from typhoid fever in Chicago in 1891 reached 174 per 100,000 population, the highest typhoid death rate of any major American city. Chicago was dying of its own sewage. The engineering solution proposed by sanitary engineer Lyman E. Cooley in the 1880s was to reverse the flow of the Chicago River. If the river could be made to flow westward instead of eastward, the city's wastewater would flow away from Lake Michigan rather than into it. The wastewater would discharge into the Mississippi River drainage system through the Illinois River, eventually reaching the Gulf of Mexico 900 miles downstream. Lake Michigan would be protected from contamination. Chicago could draw clean drinking water from the lake. The typhoid and cholera death rates would drop. The city could continue to grow. If you appreciate the depth of these American industrial heritage stories and want to support more of them, join at the Boss tier for early access and members-only polls, or Final Boss for member shoutouts and members-only videos. The link is in the description below. Now we walk through what reversing a river actually required at the engineering level. The Chicago River has its watershed almost entirely on the Lake Michigan side of the Chicago Divide, a low ridge of land approximately 3 to 5 miles inland from the lakeshore. To reverse the river, engineers needed to cut through that low ridge with a channel deep enough that water from Lake Michigan would flow naturally westward through the channel into the Illinois River drainage system. The required channel would be approximately 28 miles long, running from the south branch of the Chicago River near downtown Chicago southwest to the Des Plaines River at Lockport, Illinois. The channel had to be deep enough that the water surface at the Chicago end was lower than the Lake Michigan water level, which would cause water to flow continuously from the lake through the river system and into the channel. The required depth was approximately 36 feet below the original ground surface in the deepest sections, 28 miles, 36 feet deep, through Niagara limestone bedrock, by hand and explosive. That was the engineering challenge the Chicago Sanitary District faced in 1892 when construction began. The Chicago Sanitary District was created by the Illinois State Legislature in 1889 specifically to design and build the canal. The district had taxing authority over the city of Chicago and the surrounding suburbs, allowing it to issue bonds and collect property taxes to fund construction. The total construction budget approved by the district in 1890 was approximately $30 million in 1890 dollars, equivalent to roughly $950 million today. Construction began on September 3, 1892, with Chief Engineer Isham Randolph in charge after the original Chief Engineer Lyman Cooley resigned in 1893 over disagreements with the district board. The political battles that preceded the canal construction were intense and lasted for nearly 2 decades before construction began. The basic engineering proposal had been developed by sanitary engineer Lyman E. Cooley in the late 1870s, with detailed cost estimates and route surveys completed by 1881. The proposal required the state of Illinois to authorize a special taxing district with bonding authority to fund the construction. The Illinois state legislature debated the proposal through 3 legislative sessions before finally authorizing the Chicago Sanitary District in 1889. The opposition to the canal came from several directions. Suburban property owners along the proposed canal route objected to the disruption of their land. Downstream Illinois River communities objected to receiving Chicago's wastewater. Missouri and other downstream Mississippi River states objected on principle to having Chicago divert its sewage into the broader Mississippi system. Railroad interests opposed the canal because it would create new water-based competition for freight traffic. The Catholic Church in Chicago opposed certain aspects of the route alignment that would have required relocating church properties. The cumulative opposition delayed the project for years. The final authorization came in 1889 after a particularly severe typhoid outbreak in Chicago killed nearly 2,000 people in a single year. The public health emergency overcame the political opposition. The sanitary district was created with broad taxing authority across the Chicago metropolitan area, allowing it to issue bonds backed by property tax revenues. The district board hired Cooley as the original chief engineer. Cooley spent 2 years refining the route alignment and finalizing the engineering specifications. The construction contract bidding occurred in early 1892, with contracts awarded to a consortium of regional construction firms. I have written the full story of this down. The Erie Canal, Volume 1, The Men Nobody Wrote a Book About. Every worker in it came from the real payroll records. If you want it, the link is in the description, or scan the code on screen. Now, back to the work. The geological survey of the proposed canal route had been conducted between 1885 and 1890 by Illinois Geological Survey engineers under the direction of state geologist Joshua Lindahl. The survey identified the geology along the entire 28-mile route. The shallow surface layers were glacial till from the last ice age, primarily clay and sand with scattered boulders. Below the glacial till was Niagara limestone bedrock, a hard sedimentary rock approximately 350 million years old, formed when the Chicago region had been a shallow inland sea. The Niagara limestone was the primary excavation challenge. The limestone was hard enough to require dynamite blasting for removal, but soft enough that mechanical excavation could supplement the blasting in some sections. The geology was relatively consistent across the route, which simplified the engineering planning significantly. Unlike mountain tunneling projects where unexpected geological conditions could halt work for months, the Chicago Canal excavation could be planned with high confidence in the geology. The construction work proceeded by hand drilling, blasting, and steam shovel excavation. The crews drilled blast holes into the limestone bedrock using pneumatic drills powered by compressed air piped from portable steam-powered compressors at the work sites. The blast holes were loaded with dynamite, which had become the standard American blasting tool since the 1870s. The blasting broke up the limestone bedrock into rubble that could be removed by hand labor or by steam shovel. The steam shovels of the 1890s were primitive compared to modern construction equipment, with each shovel having a bucket capacity of approximately 2 to 4 cubic yards. The cumulative excavation rate was approximately 10 to 20,000 cubic yards of bedrock removed per day at peak operations, with the entire workforce of 8,500 workers operating across the full 28-mile length of the canal simultaneously. If you are new here and enjoying this kind of historical depth, subscribe so you do not miss the next video. We publish 2 videos per day this week. Now we walk through why no modern engineering team has replicated the Chicago Canal construction methods. The frame for this video is deliberately provocative. The title says AI engineers cannot recreate the project. The provocation has a specific technical meaning. Modern engineering projects of comparable earth-moving scope, including the Panama Canal expansion completed in 2016 and the Three Gorges Dam in China completed in 2012, use machinery and methods that did not exist in 1892. Modern projects use enormous bucket wheel excavators, modern explosive technologies, computerized survey instruments, and integrated project management software. The modern methods are vastly more efficient than the 1890s methods on a per-worker basis. Modern projects move more earth per worker per day by a factor of 50 to 100 times the 1890s rate. But the frame is not about whether modern engineering can do larger projects faster. The frame is about whether modern engineering can reproduce the specific coordination pattern of the 1890s construction. 8,500 workers laboring simultaneously across 28 miles of construction, using hand tools and primitive machinery, with the work coordinated through handwritten daily reports, telegraph communications, and personal supervision by Isham Randolph and his lieutenants. The coordination pattern required intensive labor management at a scale that modern engineering simply does not use anymore. Modern projects use much smaller workforces, working much more intensively with much more powerful machinery. The 1890s coordination pattern is essentially extinct as a working approach. Modern engineering teams have never attempted to replicate the Chicago Canal construction with the same coordination methods, the same hand labor scale, and the same constraint set. The provocation is defensible because it is technically true. Nobody has tried to build a similar project using similar methods. The closest modern equivalent would be massive infrastructure projects in developing countries where labor is cheap and machinery is expensive. But even those projects use modern construction equipment and modern project management methods that the 1890s Chicago Canal did not have. The Chicago Sanitary and Ship Canal opened on January 2, 1900. The opening was carefully timed. The Chicago River had been showing signs of contaminating Lake Michigan more severely than usual in late 1899, and the district board accelerated the opening by approximately 4 months to address an emerging typhoid crisis. The actual opening ceremony was a small affair. A construction crew opened the Bear Trap Dam, the hinged steel gate at the Chicago end of the canal, allowing water from the Chicago River to flow into the canal and westward toward the Des Plaines River. Within hours of the dam opening, the Chicago River had reversed direction. Water flowed from Lake Michigan into the river, then westward through the canal into the Des Plaines, then into the Illinois River, and ultimately to the Mississippi. The state of Missouri immediately sued the state of Illinois in federal court, alleging that the Chicago Canal would contaminate the Missouri water supply downstream. The lawsuit reached the United States Supreme Court in 1906. The court ruled in favor of Illinois, holding that the dilution effect of the Illinois and Mississippi River flows would adequately reduce the Chicago wastewater contamination by the time the water reached Missouri. The ruling was technically correct. Modern water quality monitoring confirms that the Chicago wastewater is diluted to acceptable levels by the time it reaches the Missouri portion of the Mississippi River, hundreds of miles downstream. The typhoid fever death rate in Chicago dropped dramatically after the canal opened. In 1901, the first full year of operation, the typhoid death rate dropped from the 1891 peak of 174 per 100,000 to approximately 90 per 100,000. By 1910, the rate had dropped to approximately 30 per 100,000. By 1920, the rate had dropped to 14 per 100,000, a reduction of more than 90% from the pre-canal peak. The Chicago Canal had effectively solved the sanitation crisis that had been killing Chicagoans at a rate of approximately 1,500 typhoid deaths per year through the 1890s. The canal saved thousands of lives per year through the early 20th century. The economic effect on Chicago was also dramatic. The canal allowed Chicago to continue growing as a major industrial city, reaching a population of approximately 2.5 million people by 1920. The Port of Chicago became a major freight handling facility, with the canal carrying both commercial freight and the city's wastewater. The combined infrastructure made Chicago the second largest city in the United States by 1920, surpassed only by New York City. Without the canal, Chicago's growth would have been capped by the sanitation crisis, and the city probably would have remained a regional rather than national economic center. The labor force on the canal construction reflected the broader American industrial labor pool of the 1890s. Approximately 40% of the workers were American-born, primarily from Illinois, Indiana, and the surrounding Midwest. Approximately 30% were European immigrants from the recent immigration wave, including Italians, Poles, Czechs, Hungarians, and Slovaks. Approximately 15% were Irish-American workers from the established Irish immigrant communities of Chicago. Approximately 10% were German-American workers. The remaining 5% were a mix of Scandinavian, Russian, and other European immigrant groups. The labor force was organized into crews of approximately 100 to 200 workers per construction segment, with each crew under a foreman who reported to the section superintendent. Total cumulative employment over the 8-year construction period was approximately 25,000 individual workers, with peak simultaneous employment of 8,500 workers during the middle years of construction. The wages paid on the canal were competitive with the broader Chicago industrial labor market of the 1890s. General laborers earned approximately $1.75 per day. Skilled drill operators earned approximately $2.25 per day. Steam shovel operators earned approximately $3 per day. Crew foremen earned approximately $3.50 per day. Section superintendents earned approximately $5 per day. Workers worked 10-hour shifts 6 days per week, with Sundays off. The work was physically demanding, but the conditions were better than the typical Chicago meatpacking or steel mill work of the era. The canal construction had a labor turnover rate of approximately 40% per year, lower than the industrial average of the period, reflecting the relatively favorable working conditions. The worker fatality count for the canal construction was relatively low considering the scale of the project. Approximately 70 workers died across the 8 years of construction, primarily from blasting accidents, steam shovel accidents, drowning in flooded work pits, and various crushing injuries from rock falls and equipment failures. The fatality rate of about 9 deaths per year was substantially lower than the typical American construction project of the era, which often saw fatality rates of 50 to 100 deaths per year on comparable scale projects. The lower fatality rate reflected the application of relatively modern safety practices developed by the late 19th century American mining and construction industries. The canal was the first major American infrastructure project to systematically use steel-toed boots for the labor force, electric lighting in covered work areas, and continuous safety inspection by professional safety officers. The Bear Trap Dam at the Chicago end of the canal was a particularly notable engineering feature. The dam was a hinged 60-foot wide steel gate that could be lowered to allow water flow or raised to block flow. The gate was designed by structural engineer Major John Lyle Harrington of the United States Army Corps of Engineers, and was the largest such hinged dam structure in the United States at the time of construction. The Bear Trap Dam operated continuously from 1900 until 1938, when it was replaced with a more modern control structure. The original Bear Trap Dam structural members are preserved at the Chicago History Museum. The technical lessons that the Chicago Canal contributed to subsequent American engineering practice were substantial. The canal demonstrated that large-scale earth-moving projects could be completed on schedule and within budget when supported by appropriate political will and adequate financing. The canal demonstrated that hand labor methods could be effectively combined with mechanical excavation equipment to produce results that exceeded what either approach could have produced independently. The canal demonstrated that systematic safety practices could substantially reduce worker fatality rates compared to the typical American construction project of the era. The canal demonstrated that public health benefits from sanitation infrastructure could be quantified through systematic mortality statistics. The canal demonstrated that interstate water rights disputes could be resolved through federal court proceedings rather than through political negotiation alone. The Panama Canal hand-era construction between 1904 and 1914 drew extensively on the Chicago Canal precedent. The Panama Project engineers studied the Chicago construction methods, the labor management approaches, the safety protocols, and the political financial structures developed for the Chicago project. Several Chicago Canal engineers transferred directly to the Panama Project after the Chicago Canal opened, including engineering supervisor George Gothel's deputies who had worked on the Chicago Sanitary District construction. The Panama Canal construction labor force was substantially larger than the Chicago Canal at approximately 75,000 workers at peak, but the management methods and the construction techniques traced directly back to the Chicago precedent. The Hoover Dam construction in the 1930s also drew on the Chicago Canal precedent, though less directly than the Panama Canal. The Hoover Dam labor management approach included the systematic safety practices that had been pioneered at Chicago, the worker compensation insurance system that had been refined through the Chicago experience, and the contractor coordination methods that the Chicago Sanitary District had developed. The Hoover Dam was substantially smaller in workforce than the Chicago Canal at approximately 21,000 workers at peak, but the engineering management traditions were continuous. Isham Randolph served as chief engineer of the Chicago Sanitary District from 1893 until 1907, completing the original canal and overseeing the first 7 years of operation. Randolph was born in Virginia in 1848 and trained as a civil engineer through self-study and field experience, rather than through formal university education. Before joining the Chicago Sanitary District, Randolph had worked on various railroad and canal projects in the South and Midwest. After completing the Chicago Canal, Randolph consulted on various other major American water projects, including the Panama Canal hand-era construction. He died in 1920 at the age of 72. The economic effect of the canal on Chicago's emergence as a major American city deserves more detailed treatment. The city of Chicago in 1890, before the canal was operational, had a population of approximately 1 million and a metropolitan economy dominated by meatpacking, grain trading, and railroad freight handling. The typhoid mortality crisis that the canal addressed was directly limiting Chicago's continued growth. Cities with high typhoid death rates struggle to attract continued immigration and investment because workers and capital prefer cities with lower disease risk. Without the canal, Chicago in 1900 would probably have stabilized at approximately 1.25 million population and would have been increasingly losing population to other Midwest cities, including St. Louis, Cincinnati, and Cleveland. The canal removed the disease constraint on Chicago's growth. After the canal opened in 1900, Chicago grew rapidly. The population reached 1.5 million by 1905, 1.75 million by 1910, and over 2.25 million by 1920. The metropolitan economy diversified beyond meatpacking and grain trading into manufacturing, finance, and corporate headquarters functions. Chicago became the second largest city in the United States by 1920, surpassed only by New York City. The Chicago commercial elite of the 1910s and 1920s explicitly credited the Sanitary District Canal for enabling the continued growth. The Chicago Daily Tribune editorial of January 2, 1910, marking the 10th anniversary of the canal opening, included the statement that without the drainage canal, Chicago would have stagnated at a population of 1 million people and would never have become the great metropolis of the Midwest. The sanitary district engineers and workers of the 1890s saved Chicago as effectively as any military force ever saved a city under siege. The federal court rulings on the canal's interstate water diversion deserve additional discussion because they established American legal precedents that continue to shape federal water rights law today. The Wisconsin versus Illinois case, decided by the Supreme Court in 1929, held that the state of Illinois could divert Lake Michigan water through the canal only up to a specified maximum flow rate determined by federal regulation. The decision was based on the principle that Lake Michigan was an interstate water resource shared by multiple states and the federal Great Lakes governance system, and that no single state could unilaterally divert lake water in unlimited quantities. The maximum diversion rate established by the Supreme Court has been periodically renegotiated through subsequent court proceedings and federal regulations. But the basic principle that the federal government regulates the Chicago Canal water diversion has been continuous since the 1929 ruling. The Chicago Sanitary and Ship Canal has been continuously in operation since January 2, 1900. The basic infrastructure built between 1892 and 1900 remains in place, with various modernization upgrades to the locks, the pumping stations, and the control systems over the subsequent 12 decades. The canal carries approximately 50,000 commercial vessel transits per year, plus the wastewater treatment outflow from the Chicago metropolitan area's wastewater treatment plants. The total daily flow through the canal is approximately 3 billion gallons. The river continues to flow backwards. The reversal that Isham Randolph and his 8,500 workers accomplished in 1892 to 1900 is still in effect today. Anyone who has seen the masonry on a 150-year-old canal knows this. The Chicago Canal is not just engineering. It is a particular conjunction of engineering ambition, public health necessity, political will, and labor capability that occurred in the 1890s, and that has not occurred again at the same scale in the United States since. Modern American infrastructure projects of comparable scope are rare. Modern American infrastructure projects that combine the engineering, the public health, the political, and the labor dimensions in the same configuration as the Chicago Canal are essentially non-existent. The Chicago Canal was a unique moment in American engineering history. It produced a unique piece of infrastructure that has continued to function for a century and a quarter. If this is the kind of history you want kept, the book is the place it lives. The Erie Canal, Volume 1. Link in the description, or scan the code. Thank you for sitting with these men. Before we close, if this kind of pre-modern engineering story is what you came for, the final boss tier at $9.99 gets you members-only videos plus your name in upcoming uploads. Boss tier at $4.99 for early access. Link in the description. Thanks for watching to the end. The Chicago River is still flowing backwards today, 125 years after Isham Randolph and his 8,500 workers reversed it. The American Society of Civil Engineers designates the canal as a historic civil engineering landmark. No modern engineering team has ever attempted to replicate the 1890s construction methods at the same scale. Modern earth-moving projects use machinery that did not exist in 1892. The coordination of 8,500 hand laborers across a 28-mile cut through limestone bedrock has no 21st century analog. The Chicago Canal was the engineering precedent that informed the Panama Canal hand-era construction 5 years later. The Panama Canal hand-era engineers studied the Chicago Canal construction methods extensively before beginning their own work in 1904. The Chicago methods became the standard reference for large-scale American hand-labor earth-moving projects for the next 20 years. Modern engineers do not use those methods anymore. The Chicago Canal stands as the high watermark of pre-mechanized American civil engineering. The records prove it. The river continues to flow the wrong direction. The infrastructure remains.